Hi, I'm Ari Helchuk from Root Signals. I'm going to be presenting some important and useful points about understanding, detecting, and fixing issues with large language model usage, along with our head of AI, Ous. And I will first give some general points about the kinds of mistakes that LLMs do for agents, chatbots, workflows, whatever you're building, how you can address them with LLM charges, and what is a charge in the first place. But mostly we are focusing very hands-on on how these problems occur and how you fix them. So starting first, why these failures occur in the first place. So as you are probably familiar with LLMs, since you're watching this presentation, so LLMs are fundamentally non-deterministic. They are based on statistical outcomes, and uh, you cannot fundamentally predict what they are going to tell you except by empirical experimentation and repetition. Furthermore, they have no self-reflection. They have no inherent knowledge of what they're doing unless there's some kind of reasoning happening on top of the base model. And even then, they are still liable for various problems. Furthermore, there's the kind of guidance that we tell these models might be insufficient. And this means that even if the model is perfectly fine, our guidance might not actually be saying what we think it's saying. And this leads into all kinds of problems. Now, the way in which we can find these problems automatically is by using LLM charges. So what is an LLM charge? Well, there's two ways of looking at this. So one is that any model that can take in text and output text, so any small model or large model can serve as a charge. On the other hand, if you want these charges to work in a consistent, systematic, and predictable way, then you need a framework that actually takes care of that. So you can basically ask any model, like, is this content good? Does it follow this and this criteria? But if you want that charge itself to always uh, follow these judgment instructions the same way and give predictable scores, for example, then you need a framework like root signals or something else to actually keep those charges themselves in check. So then the other dimension to look for is at a at what could be called the dedicated models. So there are also charge models that are specifically trained or specifically fine-tuned for judgments. Well, Root Signals has some. There are some open source ones, and there are other providers that have some. So for certain kinds of judgments, certain kinds of situations, you might want to use a dedicated charge model. But in general, you can get started with any common model. Uh, Furthermore, these models might be giving you scores as an outcome. They might be doing rankings, so which output is better than the other one, and so on. And for practical purposes, you can think of some models being essentially real time, so something like less than 13 billion parameter models, and some models being essentially non real time. And that would usually be something like 70 billion models and above. But of course, depends on your hardware. But this is like some kind of maybe a rule of thumb. So now that we have some idea of what the charges are, let's start going through some of the typical failure cases, and I'll cover the first ones. So the most famous failure case being hallucinations. There are several different ones. There are some that we could call type 1, which are essentially factually false assertions that the model is making. So these are assertions or statements that are neither well grounded in well known facts of the world, and neither they are true based on source materials. So this is what we could call like globally false assertions. And there's a lot of disclaimers on how well you can find these and identify these, and there are also some differences in subjective opinions on these things. But in general, if you want to automate this with an LLM charge, you need to rely on the knowledge of the world that this charge has, and you need to then rely on that fundamentally to identify these assertions, unless you have a fine-tuned hallucination detection model. And the basic outcome of this is to detect the hallucination, and usually you want to block this from being shown to the user. So let's see how that happens in practice. So, like, let's say you went to ChatGPT, you asked who is Linus Torvalds, so a famous person, and you get a reply, and then you run a charge on this, and your charge would appropriately say that this is a true assertion. So this is giving uh, value of 1 between 0 and 1. So this seems perfectly fine. So this is a judgment for global truthfulness. But then let's ask something else. Like, let's ask using SDK, we are asking here who is Ari Helchak, so that would be me. And asking this from GPT-4o Mini actually gives something that is just not the case. I am not an expert in game studies and media education, but I'm an expert and academic on other fields. So this should be false. So now running an evaluator a charge on this for truthfulness, we should be seeing that this gives less than 1. So now we are getting 0.5 for this when we run the truthfulness charge on this input and output, and we're also getting breakdown on the response. So there are no facts known to this charge model that would support this kind of reply. So as you see, sometimes this can this bad or this less than perfect output from the truthfulness evaluator can be based both on uh, factually false data, factually false outputs, or it can be based on insufficient proof, insufficient evidence for the assertions. But there's a lot of nuances to this, so we can only go through some very typical first kind of 101 cases, so to speak. Then moving forward, there's a whole category of different semantic virtues, from anything from like consistency, relevance, and various other measures that you can have for the output of the model. But maybe one very important fundamental one is also misalignment with your goals, which we are using as one example here. So let's look at this typical example where you are asking your model like something like, "What are the best laptops for a trendy 17-year-old girl?" So okay, and maybe you are not asking this, but your end user might be asking this, and it's recommending like Apple MacBook Air, HP Spectre, and so on. And this is perfectly fine unless you happen to be this company. So you don't want your chatbot to give that kind of replies. So what do you do? Well, actually, you can define a simple charge. Of course, you could define much more complex one, but just for the sake of argument, you could define a very simple charge that would actually look at the reply and see that does it actually favor my products, myself now being Acer in this case. And if you would do this on this example, then actually, uh, if we put in the response that the model was originally giving, this Apple MacBook Air and HP Spectre and so on, then the Acer promotion charge is giving zero point 0.2 because the response doesn't actually favor Acer products. So this makes perfect sense. Okay, but how do we actually use this to our advantage? So now we just got this to the point where we noticed that the response wasn't favoring our company. But how do you turn this into something that would actually be useful in practice beyond just blocking this reply? So then you can go further. Let's look at this from SDK perspective, and we can see what we can do with just using this same charge. So here we have the initial response that the model was giving. It was getting a score of zero point 0.2, and there's justification why that was. And now we run this through a remediation loop. So a relatively simple loop that actually improves the replies based on these scores and based on the justifications. And now we see that it gets to a new one, which gets 0 0.4. And then we continue, we want to go higher. The next version is actually uh, already finding, or it's already suggesting Azure Swift 5. So this seems good. This is what we wanted to get. And otherwise, the answer is still quite good. So we can see that this is actually getting 0.25, and there's an explanation for why. But anyway, the main point being that we can get this kind of outcome, and it is a fully automated process that changed the order of the reply, and of course a little bit of the wording of the reply to support our charge that actually aligns with our values. In this case, the values of the company using this chatbot that is based on this specific model. All right, so this is what we could call a remediation loop, and this is what we would use to actually not only block, but to actually fix the issue. And it sometimes works, not always, but fortunately, in many interesting cases, it actually works. So then moving forward, the third case. So unfortunately, the charges themselves might have problems. So if your charge is not reliable, then everything else is going to fail. And because this whole approach depends on the charges, this is a pretty important problem to tackle, because it's going to mislead you if your charge is giving wrong judgments, and then you're definitely not going to go anywhere with any kind of automated fixes. And also we'll get a lot of false alerts and false positives and false negatives as well. So you need to be able to calibrate the charge, and you need a framework for doing that. And let's see how that looks in practice if you are first starting with something that you want to be checking. Let's say that your LLM was giving a reply to something or any kind of output that clearly has political content, like Donald Trump's comment on Greenland, which is just citations from recent newspaper headlines, really. So if you want to prevent your chatbot from actually talking about this sort of things, you need a political sensitivity charge. So it's something that would detect the politically sensitive topics from this text. And now the trouble is that after you created this charge and it looks at this response, you only get 0.75, which might be still fine, but there is a really big question, like why is this 0.75? Because this is pretty much as political as you can get. And then there's some long explanation why that could be. But in general, if we want to understand where is this coming from, or firstly, if we suspect that actually the charge is not really doing exactly what we expect it to do, because this should be 1, then we need to look deeper into the charge. This is what you can then do by looking at where is the charge actually composed of. And we see here, like in the root signals charge example, you're seeing what is this charge doing. It's actually quite simple, but the prompt itself turns out not to be the problem. But this model is a bit suspicious. So we are using this fast mini model. And actually, now if you look at what happens in this model, if you want to actually understand how well it performs, you need to run some calibration data on it, meaning that you need to have some examples that you test it out against this model and other models. So what this calibration data means, if you parse this in human readable way, it says that when you give this kind of statement to the charge, it's supposed to give you value of 1. And now if you run this through against 3 different models, then actually you notice that when you run it through against GPT-4o, GPT-4o mini, and o1 mini, actually you see that the GPT-4o mini deviates with 0.35 from your target, but these other models don't. So it's clearly a problem with GPT-4o mini model and not a problem with this prompt as such. So as you can see here, each of these models got the same input, but GPT-4o mini was giving 0.65, whereas these other ones were giving 1. So from this we can conclude that actually the problem was that this model might not be strong enough, or it's trained in a different way from the others so that it doesn't detect these sort of things. And then you would, of course, go and run a lot of different examples of the political sensitive content, politically sensitive content against this model to see is this actually usually the case for this model, and then make your conclusions based on that. And what this would allow you to do is to actually create the appropriately operating judge that then you can rely on, and then you can actually use this judge and other judges, other evaluators, to actually make sure that your chatbot doesn't discuss politically sensitive contents or anything else for that matter that you don't want it to chat. You don't want it to chat about. And the same applies, of course, to any kind of background workflows or any kind of agents that you might be building. So the solution here is to first calibrate the charge, and then you can actually fix the real problems with your LLM-based automation. So this was my overview of a few high-level typical cases, and Oz is now going to continue and dive into some of other blunders and other more specific errors that you should be familiar with. Go ahead, Oz.
Hi, everybody. This is Oz. Thanks a lot, Ari, for the first three dropping the ball examples of LLMs, and I'll be counting from 4 to 10. And this is not an exhaustive list. I think all of us know LLMs drop the ball way too often, and these are just a couple of examples that we have seen in the industry in actual use cases, and we are basically trying to prevent that. Uh, as you are familiar with our previous webinar, I'm always head of AI, and we are deep into this LLM evals and judges at scale business. So number 4 is pretty common, is this confidentiality. I think a lot of evaluation metrics and evals platforms, they treat this kind of metrics like politeness or confidentiality in a almost in a binary way, um, especially I think confidentiality and toxicity, these sort of harmfulness evals. And it's exactly not like that actually. The reality is it's a gray scale. So you need to have such judges that can understand confidentiality, uh, concept of confidentiality in a context dependent way. This is a very useful judge because because of this very reason, you can also judge actual human generated text as well on top of LLM generated text. And this goes, we have a root judge for that. It's a judge that you can use out of the box. When you go to our platform, you can find we have tens of judges specifically trained to perform that specific thing. You can use this in our platform, but most importantly, we have a Python SDK with a couple of lines of code. I'll be also sharing that. You can use this. And now, what I mean by contextual understanding. So if you want to evaluate a text, if you build an LLM application, it's almost never that LLMs obviously fail, obviously leak information. So it's never binary. So you want to have some kind of score between 0 and 1, or some sort of grade where you can, depending on the use case, threshold it. For example, let's say you build a question answering system, basic RAG stuff, and let's say the LLM answer or a human answer, in fact, said our Q1 result uh, uh, fall below the expected forecasts. Now, if you want to judge this text in terms of confidentiality, you want to get a continuous score, not 0 or 1, because it depends. For example, our judges always return not only a number between 0 and 1, but also the reasoning, the the justification why it returned that. So here, as you can read it, it's not necessarily potentially harmful, but it can be considered slightly sensitive information. Now, let's add more context to it. Let's say we will release this to public next week, right? So we would expect the score increases because that now it's a bit more sensitive because now we gave the context that these results are not public yet. So our judges, all of our out of the box judges, are designed to perform this way. So LLMs usually, if you try to judge LLMs in a binary manner, you don't go far with that. And LLMs really need this kind of continuous scale thresholding depending on the use case. And my blunder examples from 5, 6 to 7 is, of course, retrieval augmented generation, RAG, because that's probably 70% of the use cases, to be honest, at scale in the industry regarding generative AI. Now, I think anybody who has worked with RAG, they can they can sign this statement that spinning off a RAG pipeline is very easy nowadays. You don't almost need to know anything. You definitely don't need to know any machine learning or AI. Things are commoditized to the level that you just write a couple of lines of code, if even that. But doing RAG right is very difficult, mostly because RAG has too many moving parts. So starting from how do you read the document, like super basic thing, like there are complex tables, maybe a table is broken between two pages, there are images, maybe there are diagrams and all that. How do you first of all read that? How do you embed that? Do you want the embedding to be multilingual? Do you want it in a certain format that you also want the vector database scalable? Do you use re-ranker? What is the LLM? What is the prompt? The whole thing has way too many pipelines. So doing RAG, you can build a suboptimal RAG. That's not a problem. But optimizing it, improving it, you need to measure that. So that's why we have focused a lot on our RAG specific evaluators. So I'll be just demoing in our Python SDK actually. So if you pip install root signals, we have a quick start document. In a couple of lines of code, you would be able to have measurability and guardrails to your RAG. And it goes very simply. You import our client, um, and let's simulate a RAG specific example of RAG. So this is, I just simulate here, let's say these two chunks come from your retrieval. You had your vector search, semantic similarity, or hybrid search, or maybe graph based, and you found these documents relevant. And of course, the most common and most dreadful dropping the ball is hallucinations. So I just gave two chunks example here because to make it a bit more understanding, normally you want to retrieve 20, 30, maybe a bit more chunks depending on the use case. But the topic here is pensions and pensioners. It's like a slightly factual kind of use case, statistics about pensioners in Finland actually, and average payments. How many are these people? How many of them still actually working, and things of that sort. And if let's say a user asks, is the number of pensioners working more than 100K in 2023? Um, and the response is, we have a response. You obviously want to measure that because LLMs definitely can hallucinate. And I think a lot of people try to measure their RAG system so that they copy paste something here and turn it into a question, or synthetically ask an LLM to create that question. But it almost never works like that because people don't exactly ask this factuality. So the reality, the actual context says more than 150,000 pensioners are still employed, but nobody asks like that. People ask, is the number of people working more than 100K, number of pensioners? So the LLM needs to reason a bit, and the more the LLM needs to reason, gather this info, the more likely it will hallucinate. So this response, yes, 150,000 pensioners were working in 2024, is correct, and we expect a full score of 1. But more importantly, we have the justification. We give very detailed response decomposition. So this was a core um, core statement, and this is referenced, and we give also the confidence, and we detect if there are any supporting or core supporting or peripheral assertions, and we also refer our justifications refer to the exact text. Now, um, you if we said if the LLM response was instead of 150, if the LLM said yes, but the number was wrong, so 250, we want a low score. We want to be able to detect that with high confidence, because it's actually 150. Or if the LLM hallucinates the year, we still want a lower score, because that is also that is not necessarily as bad as the first getting the number wrong, but it should still decrease the score, because um, there's no there's no information about 2024. It was about 2023. So this is our hallucination detection faithfulness um, uh, judge works. Now, another thing, of course, answer relevance. You simply want your answer independent of the question, independent of the context. You want your answer to be relevant to the question. So typically, when an LLM doesn't know something from the documents or just couldn't retrieve it, it it gives this sort of answer that the number of pensioners working this is not widely tracked and publicly available. It's difficult. However, trends suggest you're familiar with this. ChatGPT does it all the time. All kinds of LLMs does it all the time. They go they go straight to this kind of workforce longer, and this might be substantial. They just ramble on, and this if you start to do some sort of semantic similarity cosine distances, you get kind of high score, but you don't want that. This is not really a relevant answer, so I expect a low score. So our answer relevance evaluator and judge is specifically trained to capture this sort of cases. And finally, we have many more, but specifically for RAG, you if you can't retrieve the right things, after all, the LM cannot answer. So you want to able to measure context precision, context recall. And context recall is simply if you know the ground truth. So if you have an expected output of, hey, this is an expected answer, can I deduct this expected answer from my context? So this simply measures if my context is even enough to answer this in the first place. So this is completely different than our first example of if the model is answering faithfulness to the context, and you bring a ground truth. So combining these three, you can seriously quantify your RAG pipelines and optimize your hyperparameters. On top, you can also actually use these as guardrails. Moving on, number 8, repetitive output with redundant information. This is um, surprisingly common too. So typically, uh, a lot of use cases actually call LLMs in different places. For example, this kind of report generation. Lots of customers of ours create these clinical reports, medical summaries, police reports, financial reports, and there are different data sources, and you use LLMs to extract different kinds of information. So you never ask one LLM call and just dump it to the data, because there are nuances. And when you do that, this LLM response usually doesn't know the other LLM response, so you have some sort of conciseness issue, and the final report has repetitive information. The final report is uh, it's kind of, it has a lot of redundant information. And the most typical example here is you have a medical summary from patient background, um, patient doctor transcripts, medical records, and all that. And these are different LLM calls, and you create a final clinical report as such. And you want to measure if this is really concise. You don't want repeating stuff. And here, I just created a custom judge repetition evaluator. A repetition evaluator, it has a simple prompt specifically for clinical note summary. Evaluate this in terms of conciseness. Higher score means no repetition and duplicate info available, and um, lower score means there's a lot of repetition. And I'll be showing how you can create a custom judge at root signals, but it's very simple. You can also tune your judges, you can train your judges, the whole thing, and you can use our judge in Python in a couple of lines of code. But the idea here is that you want to be able to create such a custom thing, and you want your reports to be concise. You don't want it to be having you want them exactly enough information, not repeating. And in this clinical summary, if you read it carefully, uh, the patient's alcohol consumption is actually repeated several times at the top: background, daily alcohol, current problem, and other. So this information, this report actually is it has a lot of redundant information. This is not optimal. So we return actually a relatively low score for that. And with that, you can either fix your prompt, you can have a retry, you can call another LLM, you can have this fallback mechanism, or simply you can block this response because it's kind of low quality report actually. Um, Moving on, chat derailing from the topic. So this is also pretty common. So if you have a conversational agent, um, the conversation, either due to LLM or due to human, the conversation actually can drift away from the topics you want to stay at pretty quickly. If you are building some sales agents or some kind of customer support agents, you want to stay slightly in certain topics, but also when the customer wants to go a bit off topic, you don't want to shut them off either. So there's a delicate balance here, and it's impossible to get this right if you can't measure that. So this chat derailing from the topic, it's a very common blunder, and you can again actually measure and detect that with a custom evaluator. Now, um, maybe the last one, most importantly, all use cases you actually typically care about something custom. So this is, uh, I don't want to talk about certain topic, this thing to talk about certain topics. I want certain LLM to answer with a certain tone of voice. And we all know it's not enough to write them in your original prompt, because LLMs don't work that way. There are a million ways they can answer suboptimally. When your original prompt gets longer, they cannot follow instructions anymore. So you need this judge layer and guard layer. And typically, this custom thing you care about, custom metric, is something very complex. So these are stuff like, is this chatbot or application or agent uh, responding with my company communication policy? It's like super complex thing. Or is it talking too much of jargon? Let's say medical jargon. Maybe I don't want it to. Maybe I want it really technical or other way around. And I will now show you um, uh, how does how you can solve this problem. So in our platform, you can build a custom evaluator very easily. It goes like that. First, before that, I'll show you that you can just create a couple of, let's create a machine learning jargon evaluator judge, right? So you can actually bring your ground truth scores and the input text that is being evaluated. Of course, this was a great sunny day. There's no machine learning jargon, so you give a 0. So if you have this, even a couple of samples, you have something already super powerful. to calibrate your judges. And at root signals, you can simply have a ML, create a custom evaluator as such, measure ML jargon. This is my intent. And um, you can actually add this data set. I have already, oh, maybe I haven't uploaded. So let's do that. Let's simply upload that data as a test set. I can upload this CSV file. Yeah, I'm ready to go. And I create this custom judge, and I can simply select this as my calibration set. So this is my test set. I wanna test if my judge is judging properly, actually, because otherwise, what's the point if you can't trust the judge? And once you define your objective, which prompt and model to make this judge, to support, to realize this judge, it's just parameter optimization. So you can bring here very simple prompt, evaluate the level of machine learning jargon in the text. Higher scores mean a lot of technical jargon. We always return a score between 0 and 1, so you don't need to worry about that. Yeah, this is my prompt. And now you can actually select, for example, 5 different models. Let's say Mistral, we support, you can bring your own models too. Maybe we select Llama from Grok, and you can simply calibrate this thing, meaning that you can go get a coffee, and when you come back, you can decide, you can see the results of which prompt and model combination, I'm talking about the judge prompt and the judge model, is best in judging accuracy, latency, and cost. Because as you can see, you don't need to you don't need to pay to GPT-4o because it's kind of expensive and it's kind of slow. You want the deviation low. For example, Grok deviates much less, and also it's fast. I'm talking about Llama 3 running on Grok hardware. It's fast, it's good enough judge, and it's cheap. So hey, for machine learning judge evaluator, Grok is Grok, and this prompt is perfectly fine. So this is how you tune and trust and meta evaluate the evaluators itself, and you can attach this with a couple of lines of code, this judge, to measure, so that in the monitoring view you can see how your application is performing in terms of machine learning jargon or all kinds of other metrics you care about. So that was the generic blunder, the custom thing you care about. You always care about something custom. So wrapping up, LLMs behave unexpectedly. They're just inherently unreliable and hard to control. We know that. And there are infinitely many ways LLM answers can go suboptimal. You need an oversight. You need a measurement layer. And this oversight itself needs to be reliable. So you need to be able to measure the oversight as well, because they're LLM-based and it needs to be scalable. So at Root Signals, we provide a very easy way for you to make sense of all this chaotic evals landscape. Thank you very much. So I'm Oz, and our CEO was Ari, and we are ready to answer your questions if we can. I appreciate it.